Up to chapter 5, and by the way, I just want to mention, if you're on campus, you might want to come to this thing tomorrow night. If you register, that'll tell them to buy pizza for you. There will be food, there will be Pacific hackers there. It's going to be a big event. There will be lockpicking, there'll be a talk about social engineering, and I highly recommend this social networking. Get involved with Pacific hackers or a meetup or something if you want to get a job around here. Good, I'm glad to hear it, Yasmin. I highly recommend getting to know people. The Pacific Hackers is a very good group of very good people, and it's hard to get a job now because Elon Musk has started laying everybody off. So there's a lot of highly skilled people out there looking for jobs. So making a personal contact is the best way to do it. Get people to know you. Anyway, so come and join this. It'll be in STEAM 104, a new building next to the multi-use building, the brand new one. All right, good. Anyway, so let's carry on with the cryptography stuff tonight, which is here. And I just mentioned before, there's a video explaining about what the NSA has done. It's an issue that came up in previous semesters and something people often want to know. So the data encryption standard was weakened by the NSA. IBM proposed 128-bit key, but they shortened it to 64, and then they shortened it again to 56 for no apparent reason, but obviously because that's the most they could crack. They also improved it to resist differential cryptanalysis, which was a secret technique in the system, and this is what they look for. They try to achieve this: nobody but us. They want to have a system that the NSA can get into, but nobody else. And so that's why they improved it, to block another attack they weren't using, but made sure it was vulnerable to whatever attack they are using. And that's the game. And this depends on the NSA keeping secrets, and the problem is the NSA has been spectacularly bad at keeping secrets. The most egregious example is Edward Snowden, who was an NSA contractor, and he publicly revealed a whole bunch of their top secret stuff, and then had to hide in Russia to escape punishment from U.S. courts. But the point is, it proved that the NSA doesn't keep secrets successfully, and therefore how can they have a nobody but us system, which would depend on them having a secret? And after it leaked out, then Russia did this. They made ransomware that did great damage based on an NSA exploit. They found a vulnerability in Windows, and they now, a few months before this Russian worm came out, they did tell Microsoft secretly, apparently. Microsoft pushed out a patch quietly. So people that were up to date wouldn't get hurt, but a lot of people weren't up to date. And so they got hurt. So there have been a lot of scandals about the NSA not keeping their secrets well enough and letting their weapons out, which are then used against us. Anyway, so stream ciphers. We talked about block ciphers last time, and stream ciphers. We'll talk about them here. So a stream cipher, it's a symmetric encryption scheme, just like block ciphers, where the sender has to have a private key and the recipient has to have the same private key, so you must have somehow transmitted that key previously over some trusted channel. But then, block ciphers mix the key with blocks of plain text. Stream ciphers just use the key to produce a pseudo-random series of bits. So it's like the one-time pad. And in the one-time pad, I would distribute to the person at the other end a long, long one-time pad of random bits. And here, I distribute a key which they use to mathematically create a pseudo-random series of bits. That's it. And then you just XOR the stream with the plain text. So you don't need to pad anything. You don't need to fill a block. It doesn't matter how long the message is. You're encrypting it one bit at a time.
So this makes it similar to the one-time pad?
Yes. It's essentially a more efficient form of one-time pad where I just distribute a small key, and from that you can generate an infinite stream of bits. The problem is they're not completely random, of course. They're developed from that key in some way, but it's conceptually very similar. And so what you use a bit generator of some kind. Now, one technique is a deterministic random bit generator, which will take a seed, and if you know the seed, you just get a series of bits. This is what most of the random number generators in Python and other programming languages are. Right, and so stream ciphers use a key and a nonce. The key is used for many messages and is secret. The nonce changes for each message. That's why nonce means a number used only once. So you add a number to encrypt this block, then you add a different number to encrypt the next block, and so on. Now, if you were to reuse the same nonce again, then the bit stream would be exactly the same. And therefore, that's bad. Russia made this mistake during World War II. Microsoft made this error in Microsoft Office. They always had the same nonce. And if you do that, then what happens is, since you're just XORing with the bit stream, and you're going to XOR two messages with the same bit stream, I can just XOR those two messages together, and they will the bit stream will cancel out. So I can get the XOR of plain text with the XOR of the other plain text without knowing the key. Now that would still be kind of scrambled, but in Microsoft Office documents, at the time, we used a binary format where large portions of the document were just 0. And therefore, if you just XORed together two encrypted documents, a whole bunch of it would just turn readable, plain text.
Sandra,
Yeah.
terminological question.
Yeah.
Because I read that the nonce is also called initial value, but the initial value sometimes is also the seed. So are these three the same thing?
They're very similar.
Very.
If there's any difference, I can't remember it.
Okay.
Yeah.
But more or less,
For all practical purposes, they're the same. I think a mathematician would find some subtle difference. The main thing about the nonce is you have to be sure to only use it once. But the same thing's true of the IV. Yeah.
Once and public,
Yeah.
the key private.
Yeah,
and secret.
that's right. Yeah. And so anyway, we did this one last time. You have the
Yeah.
two-time pad. If you use the same random bit stream twice, then you can use many attacks, and the one we used here was the sliding attack. So there's two kinds of stream ciphers, stateful ciphers and counter-based ciphers, which are analogous to the encryption modes you talked about last time. So in a stateful cipher, you have some kind of internal state. You initialize it, then you feed in the key and the nonce, and then you update it, and you get some bit stream, and then you update it again and update it again, and there's an internal state here. So this is a lot like cipher block chaining. You make some output bits, and then you use the output of that to be the random vector for the next one and the next one. So this is like cipher blocks chaining. Counter-based, you don't need a state, you just have a counter, a series of numbers. You add the counter here to make this different than the next one and next one, and so you use the same key and nonce all the time, but the counter provides the number that keeps changing, which is, of course, I think, I mentioned for block ciphers, this is the more modern and preferred technique. All right, so you can use special hardware to do this. You can make special hardware just to do encryption, and the fastest is to use application-specific integrated circuits, a circuit that is designed specifically for this job. You can also use programmable logic devices or field programmable gate arrays, which are hardware that can be programmed temporarily and reprogrammed. And you can, of course, software implementation in a general use computer using operations like add and subtract, and it'll process 32-bit or 64-bit words typically. The hardware will work with all the bits together with just parallel lines. And it turns out the first stream ciphers required much less memory than the block ciphers at that time, so it was cheaper to implement in hardware. So your stream cipher would only need like 1,000 transistors, but block ciphers would require 10,000 transistors, so there's a time when stream ciphers were cheaper to implement. DES was optimized for such hardware, and so in the 1970s, there was hardware designed for DES. And that became the American standard. It was built into financial systems all over the place. The problem is then they found out time passed and it was discovered that it wasn't secure. In the 90s, they were able to crack it by pure brute force. So AES deals with bytes, a block cipher, and it's more efficient than DES in software. So if you consider cryptocurrency mining, which is one place where there's been enough motivation to really make people work hard at making things fast, ASIC is the fastest, 100 times faster than a CPU. GPU is in between. Anyway, so here's a shift register. This is one form of random number generator. So a left chip operation, you just take something, move it to the left. So if you start with ones and shift to the left, the one that comes off the end will be the output, that's a 1, and you shift in a 0 on the right. So you'll get 8 ones, and then you'll get nothing but zeros after that, if you start with all ones. So you can shift, and you'll get a pattern of 1s and 0s coming out. If you have a pattern like 1, 0, 1, 0, then you'll output 1, 0, 1, 0. But if you just keep padding in zeros on the right, then after enough shifts, you'll have nothing but zeros from then on. So this is not very practical. So what you make is a feedback shift register, where you're going to shift it to the left, and what pops off the left is going to be your output, but you're going to feed in a bit on the right that will be calculated from the other bits. Use the feedback function to calculate what to feed in there. So here's a 4-bit example, and the feedback is going to XOR all the bits. So you start with 1, 1, 0, 0, you shift it to the left, this will output a 1, but the new thing you feed in on the right will be a 0, because if you XOR them, that means if there's an even number of 1s, the answer is 0. If there's an odd number of 1s, the answer is 1. So you shift this to the left and add a 0, now you get 1,000. You shift this to the left and add a 1, now you have 0001.
Oh, but
Because this one went off the end.
One because it's the result of the XOR.
Yeah. And so now you shift this to the left, and again you're going to get a 1, so now you have 0011. Now you shift this to the left, now you're going to have a 0, and so on. So it does create a pseudo-random series of bits, but now it's going to repeat. You're back to 1100. So this is the entire loop, only these 6 values. It's going to go around in a loop. And so here's the entire path of this. If you start with one of these values, you go around this loop. There's 3 loops, each with only 5 values. And then 0 just puts out nothing but zeros. So that's the available bits you can get out of that feedback shift register.
Well, for a 4-bit register.
Yeah, this particular 4-bit one where you XOR all 4 bits. You can make different ones. You could make one where you only XOR some of the bits in the state. The longest possible period is 2 to the n minus 1, because if it's all zeros, then no amount of the XORs will always be 0. So this one is always sitting alone. So the best you can do is all these would be one big loop. And this is not the best.
This is equivalent, so here the goal would be to maximize the period.
Yes.
Which is in a sense analogous to what we said a couple of times ago, creating an algorithm that pushes the attacker towards the brute force.
That's right. That's the idea. Yeah, that's the best you can do here. All right. And
so this approximates the brute force. So this is the
yeah, that's the idea.
Yeah.
The Optimon would do that. Now, have I still the power adapter? Okay, fair enough. All right. So that's a linear feedback shift register. Here's another one where we're only going to XOR bits 1, 3, and 4, not bit 2. So that's where these ones are. And that one is 0001. Yeah, the 1 and these 2 will give you 1. The 1 and these 2 will give you another 1. The 1 and these 2 will give you a 0. This 0 and those 2 will give you a 0. This 0 and those 2 will give you a 0. And this will give you a 1. So in this case, you get a period of 6 instead of the period of 5 we had last time. So it's another way to do it.
Can you go ahead?
Yeah.
Why the?
Because you
Why
only.
the third one gives you 0 if it is a?
Because you only do 1, 3, and 4. You don't include this bit. So counting from the right, yeah, you only use some of the bits, and therefore that's the way you can make different ones, and some of them will be longer. So here's one with the maximal period. If you XOR only bits 3 and 4, that will give you the maximal period, just these 2. This will be 0, this will be 0, this will be 1, that'll be 1. And that one, here's what it'll do. It'll take you all the way around this. You'll have to go 15 times to get back where you started. So it's not obvious at all, but XORing just these 2 bits is the one with the maximum period. So that's the sort of thing you can do. So all these things are very insecure, however. For one thing, I have this obvious period, but it's even worse than that. It turns out that all you need to know, if you have 4 bits, is you need to know 4 numbers, and you can figure everything out. Because, of course, that's enough to sample all 4 locations, and you can decide which way it went. So it turns out these things by themselves are not very good, and there is an algorithm designed to solve the equation. So to make them a better bit stream generator than that, you pass it through a nonlinear function that will do something like AND and OR along with XOR, like this. So L1 and X2, XOR L1 and L4, that kind of thing. This nonlinear operation will help prevent people from calculating the hidden function from the output. So G function hides the linearity of the system. It turns out it's better than linear feedback shift registers, but it's still breakable by more complicated attacks. More clever mathematics can still get in. So nonlinear feedback shift registers, you replace the function with a nonlinear function that is complicated like this, mixing AND and OR and XOR. This makes it very complex to attack or analyze. There's no way to calculate the period. There's no way to prove the period is maximal. Combining a linear feedback register and a nonlinear feedback shift register, there you can get the maximal period, because this one you can arrange to have the maximal period, and this one you can have cryptographic strength. So combining the 2 together is what's recommended. That's what I think your textbook author wrote this one, Grain 128. So you have a 128-bit linear feedback shift register, and you have a 128-bit nonlinear feedback shift register, and you combine them with a filter function. So this is the modern technique. You combine both of them, and now you can get a really long series of apparently random bits. And there's no known way to calculate the key from the bits that come out. And so you can prove, since you have the linear part, you can prove that it won't repeat except for maximum length. And so it takes a 128-bit key and a 96-bit nonce. And it's got a plan here, just a linear, and then it's got the feedback function. And here's the linear feedback function, which is pretty screwy. The 32nd bit, 47, 58, 90, 121, and 128. How they figured this out, I don't know. And the nonlinear one is even more of a mess. It's groups of them with, I think this means XOR and this means AND or something like that. So it's a very screwy.
The plus is the OR.
Plus is,
The end is
your plus is XOR. Right? Plus is XOR, and no symbol is AND, I think. Yeah, let's go back.
The AND because it's multiplication.
Yeah, it's going to be, yeah, AND. AND isn't, when they're just rammed together, that's AND. So that's it. So the plus is XOR, and the two rammed together are AND. So this is the nonlinear function. This one and that one and that one, then XOR these others. So that is the particular function that is the nonlinear feedback function, and combining both of these, you get what's considered a very good one, even today, Grain 128. So it was proposed in 2006. The original version had a side channel fault attack. So if you could trick the processor into making a mistake, that's a fault attack, then you could leak out some data. So they improved it with Grain 128A, and that seems to be holding up very well. It's the new, most highly recommended system. Now there's another stream cipher used in the 2G mobile standard called A51. They kept the algorithm secret, but eventually, and there were some NATO signal intelligence agencies that wanted to keep it weak so they could snoop on phone calls. And then we had a deliberately weakened version for exports, which I mentioned last time. In the 80s and 90s, the US government pushed weak cryptographic export. So they poisoned the internet with all these machines that could only use bad encryption. And they did the same thing with phone networks. A51 design leaked and it was reverse engineered. And as in 2014, there were 7 billion customers counting on it. It turns out to have serious security weaknesses, and the NSA can routinely decrypt it. So it's pretty weak. And they worked with 3 linear feedback shift registers using these functions. So it's a whole lot simpler than Grain 128. See, it's just, you take the key, which I think is 64 bits, and you break it up into 3 bits, 23, 22, and 19, and each of them is pretty simple, and then you combine them. So one trick is you don't update all 3 at each clock cycle. You only update one of them at a certain time. So these 3 functions only update in a staggered semi-random order, which helps make it more chaotic. They use certain bits to decide which one of these to update per cycle. So it's pretty complicated, but it turned out not to be complicated enough. And the simplest thing, we did brute force attack. Since it's a 64-bit key, you do 2 to the 64 operations, but there are faster attacks against A51. There is a subtle attack, and there's a brutal attack, which you can use on it. The subtle attack, you brute force the internal states one by one. Remember, it really is 3 small problems put together, and if you can brute force them one by one, then of course you only need to do 2 to the 19, 2 to the 22, and 2 to the 23. You never really have to do 2 to the 64. That's like a meet in the middle attack. If you can somehow attack just a part of it, then it'd be pretty easy to brute force. And that turned out that you could do it. That slowed it down to 252 instead of 2 to the 64. And here's the example of how they did it. 2 to the 19, 2 to the 22, 2 to the 11, reconstruct the initial state, test whether your guess is correct. So this is a little more complicated than the meet in the middle attack for double DES, but it's similar. You're able to do it without really having to ever really do 2 to the 64 calculations. You can do 2 to the 52, which is still quite a bit, but it's achievable. That's the subtle attack. And then the brutal attack, you're going to do 2 to the 64 calculations, but what you do is you use a time-memory trade-off to make it more practical to do 2 to the 64 calculations. Now, if you're going to pre-calculate all 2 to the 64, that would take 256 million terabytes. That's more memory than you can get. But what you can do is you can make a smaller lookup table that does part of the calculation in advance. So in 2010, they took 2 months to pre-calculate a 2 terabyte table in RAM, And then using GPUs, they were able to decrypt in near runtime, in near real time, with a lot of GPUs and a huge lookup table. So, 2 to the 64 is just not enough. So it's obsolete, it was abandoned. 3G uses a Kasumi block cipher, and that's better, but people are concerned that the NSA put a backdoor in it. That once you've been caught doing that a few times, nobody will ever trust you again. And that's what's going on with the NSA. A lot of people are very worried that the NSA is backdoored anything they approved. That's why the runners-up are used by many people who deliberately do not use the official approved one. They use one of the ones that lost, which is probably just as good, but has not achieved approval by the NSA. And you could argue that might be the most secure thing to use. By the way, even though China is making their own systems now, I assume that their equivalent of the NSA has probably backdoored it too. I wouldn't use the one officially approved by the Chinese government either. So anyway, let's take a look at a Kahoot. It's 5A. But I assume they're just as anxious to spy out everything as we are. See you're in. I'll wait a little bit longer to see if more people are coming. That's true. We don't get any more. But it's a review. I think some people don't dare to compete. They just want to watch. The customer is always right. Anyway, all right. So. All right, so what Stream Cipher uses init and update functions. That's the stateful one. Good, everybody got it? You initialize the internal state, and then you keep updating the internal state as you pump out blocks of bits. There you go. All right, so which cipher was designed in the 70s for hardware? That was the infamous DES, the one that was approved and used for decades, but ultimately proven to be very insecure, and we had to abandon it in the 90s as the US government got very humiliated by trying to get us to use a 56-bit key, which is just too small. All right, which system can be broken with the Berlekamp-Massey algorithm? Yeah, the linear feedback shift register. You can predict everything from a certain number of samples with that. All right. And which system uses both an LFSR and an NFSR? Yep, that's grain, the new hotness, the new stream cipher. Might be enough of unique identifier. Good. So, So let's go on here. So the software-oriented stream ciphers will be efficient if they work with 32 or 64-bit words. That's normal for modern CPUs. That's their natural processing size. Now the problem is block ciphers suffered from padding oracle attacks in CBC mode, so that made them fall out of favor, and people have decided to move back towards stream ciphers. They've gone back and forth several times, as we'll see. RC4 was a really popular stream cipher, divided in '87 by Ron Rivest, who is part of the R in RSA. He's invented a whole lot of modern encryption things. Very important engineer. It was reverse engineered and leaked in '94 and was very widely used until 2015, used in WEP and TLS. But it was ultimately found to have serious security flaws and has been essentially abandoned. It is amazingly clever, however. And you see, around 2014 and 2015, 2016, everybody gave up on RC4, deciding it had too many flaws. But it's incredibly simple. It has an internal state of 256 bytes, and it starts containing all the numbers in order, from 0 to 255, and all it does is shuffle those values around like a deck of cards. No XOR, no OR, no AND. It's very strange that way. So what you do is you have a key, you have an n-byte key, and you calculate an array from an n-byte key. You set this to that's the initial array, and then you just keep swapping pairs of them. So you flip two of the cards, then you swap two other cards, then you swap two other cards, and you do that a lot of times. 256 times you swap all the cards, and the key is calculated. From the key, you calculate a pseudo-random series of numbers here. Which cards to swap. So it's like shuffling a deck of cards. You're just swapping two cards, and the pattern of which cards you swapped is determined by the key from some function based on the key. So getting the key stream, you do this. So to encode plain text that is m bytes long, you generate m bytes of key stream this way, and then you see the function S of the function SI of SJ %256 is combining 2 bits. And so you generate key stream with this operation, which is a little screwy, but the main thing is just flipping those bytes around. And that turned out to be enough. So it's sort of screwy, but that's how it works. And it was used to encrypt a lot of things with a stream size. It doesn't have a nonce at all. The key is all you use. So if you were to encrypt something else with the identical key, it would be completely an identical bit stream, and it would have the flaw we had with the 2-time pad. So what WEP did, and by the way, this is a really bad idea, is they took the first 24 bits of the key and treated it as a nonce. This is a no-no. When doing encryption, you don't want to take any part of it and use it for some other purpose. You'll generally be sorry. So using part of the key as a nonce, this turned out to be too short, because if you have 2 to the 24 possible keys, then if you just randomly, after 2 to the 12 encryptions, you'll have a duplicate nonce. And once you have a duplicate nonce, that means the key stream is duplicate. So you have 2, if you were to use wired equivalent privacy for network packets, you only need 2 to the 12 packets before you'll get 2 packets that are encrypted with the same key. And what's even worse is in wireless networks, you can pretty much guess what most of the plain text is, because in wireless networks, most of the packets are ARP packets, and those are also the shortest packets. You can easily identify them, and most of them are completely predictable. It's who has 192.168.101, tell 192.168.1.102. Most of the bits in that are in fact always the same. So in fact, you can easily pick out stuff, and you pretty much know what a lot of the plain text is, and you can find 2 of them encrypted with the same key stream, so it's really easy to use them to exclude a whole bunch of the key space. And that's how the WEP attacks work, and there's a whole series of them. You don't need to try all the possible keys. You can quickly find patterns in some of the outputs that make it possible to lower the number of keys. And so web attacks appeared just 2 years after it was approved, and many stronger attacks kept coming over and over until there were faster and faster ways to get in. My students used to do it as homework 10 or 15 years ago, and you could crack into WEP in about 5 minutes on a normal network. Anyway, so in TLS, they didn't try to add a nonce, they added a session key. And here they had another flaw in RC4, which is really fatal, which is, I think, when people gave up on it. It turns out that this shuffling stuff is not really random. It turns out the second byte is 0 twice as often as it should be. So that means it isn't really shuffling those cards completely randomly. That turns out to be incredibly messed up. And it eventually proved that all of the first 256 bytes are biased. They are not evenly distributed. And that means there's an unbelievably simple attack. The most likely value of the first keystream bytes is 0. And you're going to XOR that. So the most likely output is equal to the input. So all you have to do is collect millions of encryptions of the same plain text, and the most common byte will be the plain text itself, unencrypted. Because it's more likely to be 0 than it is to be any other particular number. So that's an incredibly stupid attack. But if you just collect millions of them until you have a good statistical sample, most of the bytes are equal to the plain text bytes. That's not the most powerful attack, but it is the easiest to understand. And there's just a whole series of them. Every year or two, another one would come out. More and more of these attacks. Every DEF CON, you'd have guys showing off the latest RC4 attack, and they were all, you typically were cracking TLS, and they usually took like millions of encryptions of data on TLS, but there was a way to get in. And so the last one was RC4 No More, the one that got a lot of, one of the ones towards the end when we were finally giving up on RC4. And this one here, they were able to decrypt an encrypted cookie value in 75 hours if they could make 4,000 requests per second. So it takes a while, but it doesn't take forever. And it doesn't take like a super powerful computer or anything. And it's intolerable to use this kind of encryption. That's not acceptable. People can get in just a few days of hacking on it. So that's when people gave up on it. And yeah, go ahead. Yeah.
No, because it's from the first slide that you showed here in the second one. When you say that software stream cipher work with both bytes and D-word. When I say D-word, I don't have to think about assembly language, right?
No, that's the word. D-word is just a word of the size of the processor, 32 or 64 bits typically. Yeah, that's all it means. Yeah. Good. Okay. Yeah, and that's the same thing it means in assembly language too. It's the word size. It's how many bits each operation works on. Yeah.
Right. No, I understand that.
Yeah.
That's why I'm saying in this particular for this particular topic, when I'm dealing with this software cipher, stream cipher, am I entering also into the realm of assembly language?
Well, it's all running in machine code, which you can see as assembly language, but it doesn't. You don't need to really worry about that. Yeah. That's right. Yeah. All right. Anyway, so
very important for the analysis.
Yeah, no, just that they are designed to run on general purpose processors. That's all. The previous ones were designed to run on hardware specific, which both of them can be done either way. Mathematics is the same either way. It's just a practicality issue.
No, I understand that.
Yeah.
The bit versus byte.
Yeah. So anyway, the new one is Salsa 20. This is a new one approved by European competition to find secure ciphers, and Salsa 20 was considered to be a good one. And so what it does, it takes 512-bit blocks of plain text. There's an incrementing counter. Each block is encrypted with a key, nonce, and a counter. And it adds the original secret state to the output and XORs that with the plain text. So it's a stateful encryption scheme. And it transforms 4 32-bit words separately here with left shifts. Left rotated by the specified number of bits. This is 3 arrows to be rotating. So you rotated bits to different amounts and add them together and then XOR them. This is the quarter round function that sort of encrypts 1/4 of it at a time. Remember, the Feistel encrypted half the block each time. And this encrypts 1/4 of it each time, but each quarter is encrypted separately. So it all gets encrypted with each cycle. And again, this is sort of like just shuffling the bits according to a particular pattern. Yeah, so it's 4 32-bit words, and there's bitwise rotation, like I say. So if you rotate this by 8, then it will take 1, 2, 3, 4, 5, 6, 7, 8. That'll move because it's 8 bits. Well, I'm looking at it. You're going to shift by 8 bits. Right, so it's going to move the 7 over 4 bits would be 1. These are nibbles. This is hex.
These are nibbles, right.
So 2 over. So you move the 7 over 2, and you take the 0, 1, and move them around to right. So that's what you get by shifting over 8 bits. And shifting over 16 bits, you get this. And shifting 22 bits, you'll get different numbers all around because you shifted it within it. It's not a multiple of 4. So this is what you'll get with those kind of bitwise rotations. And where do we get CompTIA vouchers? As far as I know, you can't. The only way I know to get them is from Steve Nelson. You should contact him, the guy that did the job fair. I think he has some.
So basically, rotation. The difference between shifting and rotation is that in shifting we would have added 0.
Right, and some part would just go off the end. Yep.
Okay.
Yeah, that's the difference. Yeah. Good. And so it has a 512-bit state, and you have the initial state. You put in key. Here you put in counter where the C is, and you put in nonce. There's nonce in here too somewhere, and there's fixed constant words. So you make this 512-bit state out of all the various inputs: the key, the nonce, and the counter. And then you're going to scramble each of those things with these quarter round functions. So that's what it does. It's just a way the key is used, and the counter, and the nonce to create a pseudo-random pattern of bits. And so you get, that's the plan. And then you run it through many rounds of all this. Salsa 20 uses 20 rounds. There's another variant that uses 12 rounds. And nobody's been able to crack either of them at all, just like we talked about AES. If you shrink it down to 8 rounds, then they have some published attacks that can do it a little bit faster than brute force. But there are no known attacks against the larger version. So, it's very good. It's considered a good, we wouldn't be talking about it otherwise. It's probably the logical replacement for AES, but AES is the approved standard. There's nothing really wrong with it. That's why the stuff most people use is the official government improved stuff, like AES and RSA, which was approved decades ago. So we are still using them, and they're the standard, but they're not really considered the best anymore. There are new ones that are considered superior, which is like Salsa and the other one we talked about earlier, Grain 128, but nobody's using them very much because they are not the official standard. But technically, they're probably better. So we might switch to it someday, just like we might switch to the metric system someday. But just like the inches and feet, we have established this old system that is good enough, and bothering to switch just never seems to be worth it very much. So some new products may use these new ones, but most products will probably use the official government approved ones to make sure they can sell to the government and the military.
In each round, we add a layer of nonlinearity then?
This is a highly nonlinear operation, all this rotating stuff. Yeah. Not at all simple like XORs. Yeah. All right, and so, all right, so things that can go wrong. If you use the same key and nonce twice, then of course you've got two things encrypted with the same key stream, and that's just like the 2-time pad. We know that's bad, and that happened a few times. Also, you just have a bad implementation. There was a malicious coding contest where they did a code for RC4. You can write code that has a subtle defect. This code has a subtle defect that it will gradually destroy the state and stop encrypting. And it's not obvious, but it's very easy for your coders to make a mistake that will have some defect. This keeps happening. And of course, you can have weak ciphers baked into the hardware. This is the problem. People use deliberately insecure export ciphers. And then once you have that, once that becomes the standard, then people keep using it. This is the problem. And so there were satellite phone calls that being encrypted in fractions of a second because they designed this stuff and they wanted to sell it to other countries. So they used the export cipher. And then they sold it everywhere with the export cipher in it. This is what I see most commonly, is people just don't audit their cryptography, so they use whatever's convenient. And if it looks kind of scrambled, they say, well, that's good enough. Like I say, most Android apps use AES, but they hide the key on the phone where you can find it. So it looks encrypted, but it might as well not be. But obviously the manager never audited them. That's why I say managers should ask simple questions, and you should demand clear answers, like, what did you do with the secret stuff? If you encrypted it, where did you put the key? And if you have some complicated answer that makes no sense, that's not good enough. There should be a simple answer I can understand to where is the key? That sort of thing. Anyway, now a lot of people, I think Americans are afraid of math, so they feel intimidated. But if you're the manager, you should demand Steve Jobs was good at this. Steve Jobs would say, I want it to be easy to use. Don't give me complicated bullshit. You're the technician. Make it easy to use. Make it so I'm going to push this button, the right thing happens. And then you say we got to have like system restore and whatever Microsoft has, last known good configuration. He said, no, make it so it doesn't crash in the first place. That's what you should do. And he was not technical, but he was insistent at making it good. And he said, I pay you guys money. You're a genius. Make it work. Don't give me this complicated crap about why it doesn't work. So I think people should take that attitude about their encryption. And obviously they don't. Obviously they just take whatever their developer tells them it's encrypted. They say, oh, it's encrypted. I don't dare look at it because that's math, and math is scary. So, don't be afraid of math. You don't need to be a math genius.
This should be professionals, no?
Well, I know, but people obviously are not auditing their encryption. They're making stupid mistakes over and over. And so they need to get over it. It's not any harder than networking or anything else, or making it fast, or getting rid of memory leaks. You should not be afraid of the math. But Americans tend to be afraid of math. They need to get over it. Anyway, I get a lot of students that are afraid of math. I say, the fact that you couldn't do it in fourth grade doesn't mean you can't do it now. It's no harder than anything else. Just try it again.
Right. But also if you're going, it's hard for me to believe that, a professional cryptographer is afraid of math.
No, but most companies don't have a professional cryptographer. They have a developer, and then they say encrypt it. In fact, and they use some kind of default system built into their development environment, and they don't know enough to know that it's not working. And apparently, the customer doesn't audit it or ask questions. Everybody just assumes it's good enough, for Android apps anyway. And, that's ridiculous. Yeah. Yeah. But Matthew Green says if you get a degree in real cryptography, he says his students are in high demand. They get hired right away. People would like to hire a real cryptographer if they could. And my class is not making you a real cryptographer, but it is hopefully making you an engineer more aware of how cryptography works. He has like a master's program in mathematics where you really learn cryptography. And, that makes you a very desirable person to hire. Oh, I think companies, not just government. I think many companies, anybody developing anything would like to actually have a real cryptographer to make it secure.
In the end, most of the math that the cryptographer uses is discrete math.
Yeah, it's all discrete math, and it's state machines, yeah.
Because at the end, if you have a higher polynomial, you use derivatives to lower the degree of the polynomial, but more than that, it seems to me.
Yeah, but everything is digital here, yeah. Yeah, that's right. It's all discrete math. All right. Let's see if we got any more competitors. We may not. I guess not. We'll carry on. All right, so which system inserts a nonce value into the key? WEP did that, which is a spectacularly bad idea for many reasons, but one reason is the nonce is not secret. So now you've exposed part of the key. But anyway, that's what WEP did. Took the first 24 bits of the key and called it a nonce. All right, which system uses the quarter round functions? That was Salsa 20. All right, which one used the session key to protect cookies? That's a net plus question. That's TLS. That's how HTTPS works. You negotiate a session AES key, and then you encrypt all your traffic with that. All right, and which one has 12 or 20 rounds of calculation? That's Salsa 20, has a 12 and a 20 round version, both of which are currently considered unbreakable. All right.